All right, let's get you these answers so you know how you did on your quiz. Grades won't be going until after everybody has taken the quiz, so we can apply curve appropriately if we need to do that. All right, these are all in random order, just like for me, just like it is for you. So we're just going to go in this random order. Multiple choice section is first. All right, predict the changes in equilibrium position for this reaction. This is a reversible reaction. And it is, we're told that it's at equilibrium. What that means is the forward reaction is, the rate of the forward reaction is equal to the rate of the reverse reaction. And this question is all about Le Châtelier's principle, which says if a stress is added to a system, applied to a system, then the system will try to undo that stress. Okay, removing oxygen. So if we remove oxygen, if we decrease the concentration of oxygen, when this is at equilibrium, the system will try to make more of that oxygen that was removed. So we can do that by producing more of it, so it'll shift to the left. Increasing pressure. Pressure is caused by the collisions of gas particles with the container. So if we increase the pressure in the system will try to undo that or decrease that pressure, and so that's going to favor the side that has fewer gas particles. So over here on the reactant side, we have a total of 5 gas particles. The 4 plus the 1 is 5. And on the product side, we have a total of 4. 2 plus 2 is 4. So if we increase the pressure, it's going to favor the side that has less gas particles. It's going to shift to the right. All right, now if we had decreased the pressure, it would shift to the left. All right, adding water. H2O is a product, so if we increase the concentration of a product, the system will try to remove it or decrease it, and it can do that by using it to make more of the reactant. So that's going to shift to the left. And adding a catalyst does not affect the equilibrium position. It does increase the rate of the reaction, but it will increase the forward rate as well as the reverse rate. So it's not going to affect the equilibrium position. Decreasing temperature. So this is not proper to write it like that, but it's often written like that to make it convenient to solve these types of problems. This is just saying this is an exothermic reaction, because exothermic reactions produce heat, so they're just treating it as a product. Okay, and if it was endothermic, it would have you could have written heat as a reactant. All right, so if we decrease the temperature, we're decreasing the heat, so the system will try to adjust so more heat is produced. In this case, it'll shift to the right. All right, let me see if I read that all correctly. I think I did. Let's move on. 2 opposing reactions occur simultaneously at the same rate. Well, that's equilibrium. This is also a reversible reaction, it's told there, which means the products can make the reactants in reverse. This is also at equilibrium, so both of these statements are true. Whoops. Which statement describes what happens at equilibrium for the following reversible reaction? At equilibrium, the forward reaction stops. No, that's static equilibrium, and that's static equilibrium. So equilibrium is dynamic equilibrium. This is right out of your notes. I think this is also right out of your assignment. Let me just believe. Right there, just right from question number 3 from your homework is just the same question. All right, so well, that's also false. Both forward and reverse reactions continue, but they continue at the same rate. That's known as dynamic equilibrium. All right, change in the pressure can cause these always true, sometimes true, never true are usually, I think they've always been just copied from your worksheet, from your, whoops, that was your quiz. Let's see, here we go. So let's go to the true and false section. It is number 13. So it is sometimes true. The answers are provided for you on these worksheets. The reason it's sometimes true is because you may not have different numbers of gases. So you might have the same number of gases on both sides reacting in the product. In that case, increasing or decreasing the pressure is not going to shift the equilibrium. But it will if there's more number of gas particles on one or the other side. All right. What is the effect of adding more CO2 to the following? All right, so continue with Le Châtelier's principle. If we add more reactant, the system will try to use it up because you're causing a imbalance or stress to a system that's balanced at equilibrium. So once you're increasing the concentration, it's going to use it up to try to undo what was just applied. All right, so it's going to shift to the right. Well, there will be no shift. Well, that's not right. More carbonic acid is produced. So that sounds good. More water is produced. No, water is going to be used up as carbon dioxide is being used up. The pressure will increase. There are no gases here, so it's that's not going to be the best answer here. Including on top of that, it's yeah, okay. All right, next one. What is the expression for Kc? The equilibrium constant expression is big K is equal to the concentration of the products, which is products here on the right side is going to be a concentration of hydrogen raised to the coefficient. It's 2, so we're going to raise that to the second power, and then O2 is concentration of O2 raised to the first power, all over the concentrations of the reactants, and these only apply to gases and aqueous species, which they all are. H2O2 is hydrogen. Oh, sorry, not H2O, and raised to its coefficient is 2. So there we have it. By the way, these are products, so there's just, you can put a plus times there, multiply symbol there if we have to. So what do we see here? This one. Okay, choices all shuffled too, so it may not have been in that position for you on your quiz. All right, moving on. What is true for a reaction at equilibrium if the K value is really, really small? It's a really, really small number. That's point. Well, let's go this way. All right, that's a 2 decimals there for the 2. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. I think I lost track, but all of these zeros. Is that a big number? No, it's a very, very small number. All right, so what would cause a Kc value to be very, very small? Right, well, it would be very small if the concentration of the products are very, very small, and the concentration of the reactants are very, very large. All right, so this would favor the reactants. Is that a choice here? Nope, not both. All right, there we go. Let's just read through the rest. Okay. Which statement best describes a chemical reaction at equilibrium? Another just defining question. Concentrations of reactants are greater than the No. Concentrations of reactants are the same? No. All right, it's all about the rate. There it is. The rate of the forward and reverse reactions are the same. All right. These are your open-ended problems. Okay, let's calculate Kc. We're given all the concentrations at equilibrium, so that's just plug and play. These are the ones we love. These are the no ice boxes for this problem. Yay. So let's just let's set up our expression. It's going to be the concentrations of the products. In this case, it's going to be NO squared times the concentration of chlorine is the other product. All over the concentration of the reactant is NOCl, and that's going to be squared as well. All right, they're all gases, so they're all going to be included in this expression. All right, like we said, let's just plug and play here. All right, so we're given a NOCl that goes right down here. So I'm just gonna just rewrite it again. 0.30. This is molar because this a 1 liter flask concentration is. It doesn't matter because Kc doesn't have units anyway. So, but anyway, we're going to need to square that. All right, and on the top, let's get 1.2 up here. Square that, and then concentration of chlorine is 0.60. All right, so let's punch these numbers in our calculator. Oh no! Turn my phone. Hold on. No, I almost turned my phone off. Okay, here we go. 1.2 squared times 0.6 divided by 0.3 squared. 9.6. So our answer is 9. What is? It's Friday. My board is dying on me. 9.6. There's no units on this. We need 2 sig figs because all our measurements are 2 sig figs. So there it is. Now, if you were like really close and looked like just made like everything was good, but a careless error, I looked through your scratch paper if you had one, and I gave you half credit if everything was set up right and it was just a careless mistake. Okay, next one. The following is a reaction at equilibrium. Of course, this quiz is called equilibrium. The equilibrium system contains everything's at equilibrium. Again, these are the ones we love. It's just plug and play. Plug these in and just calculate them. All right, so let's set up the expression. Hold on, we're given Kc this time. Right there, tells us Kc is 2.2 times 10 to the 2. That's just 220 is equal to the concentration of that's what we're looking for, the concentration of the product. So let's just call that X. We're just looking for that. And the concentrations of the reactants are given at equilibrium. Very nice. We love those. All right, so now CO is just going to be what it is. All right, we know they're not going to get units. I won't write them in. But the concentration of H2 is we're going to square that because of its coefficient. All right, 0.60 squared. All right, now don't forget your parentheses when you're. Oh, hold on. What am I saying? All right, so we can just cross multiply there, get rid of the fraction. All right, and then we'll have our answer. All right, I don't have a graphing fancy calculator, so I'll just turn this into 220 first. That will make it easier for me. All right, so 220 times 0.02 times I gotta square that, 0.6 squared. Okay. And how many sig figs? All our measurements have 2 sig figs, so our final answer has to have 2 sig figs. 1.6. The number on my calculator is 1.584. Write that a little neater. All right, but we're gonna trim that off to 1.6. The unit for concentration is moles per liter, or just molar concentration, and there's our answer, 1.6. Right, I think you lost like half a point if you didn't have the units correctly, or if you didn't get the sig figs correctly. And again, if you got everything set up right, just look like you just made a simple punching in your number in the calculator, some kind of thing. I got you half credit if you had your name on your scratch work there. All right, bonus question. This one I believe is a bonus question because you need to use an ice box or an ice table. So, yep, because you're given initial conditions, that's when you need an ice box, ice chart. All right, so let's set this up. I'm just going to rewrite everything here a little, so I have a little bit more room. All right, H2 plus Cl2 is going to give us 2HCl. All right, so this is my reaction. All right, ice is initial, change, and equilibrium. All right, let's see what we're given. This is all in a 1 liter container, so that's convenient. That means everything in moles is just molar concentration again. So that's H2. So that's initially we have, I'm going to use a different shade of color. All right, so we get initially 1.10 moles per liter concentration of H2, and we're also given the same thing here, 1.10. They're added to the container. That means there's none of this stuff here yet. Initially, there's no products. It hasn't started yet, excuse me. What's the concentration of? This is what we're looking for at equilibrium. Okay, so we know the change, the reactants are going to be used. So I'm going to use a negative X for H2. I'm using the coefficients here to 1, 1, and 2 to get the ratio of the change, right? So for every H2 that's used, a Cl2 is also being used, and 2 HCl molecules are being made. Oh, what am I doing? So there's going to be 2x. And I'll put a plus sign there to emphasize that that's being produced. All right, so remember, equilibrium is what you start with plus what happened, what the change was, and then you'll get your equilibrium. All right, so 1.0, almost made a copying mistake, 1.10 minus x, because we're adding a negative, so it's going to be 1.1 minus x, and this one's going to be 1. Same thing, 1.1. Get that 0 in there, minus x. And then over here, 0 plus 2x is just 2x. All right, we're trying to figure out what x is in order to find out to answer the question. So, but at least we have one variable instead of, like, if we didn't do this, we would have to we would need we would have 3 variables, because Kc, by the way, is given to us 16. So I'm just going to do 16 is equal to the concentration of hydrogen chloride gas, so that's HCl squared, over the concentration of H2 times concentration of Cl2. All right, so we have 3 variables here, so we can't, we need to cut that down to 1. So let's just plug and play here. Now we can do that, because the whole point of the icebox was to get the concentrations at equilibrium. That's the only Those are the only values we can use in this equilibrium constant expression. All right, so we're just going to plug and play from here. It's 16 is equal to 2x, or hold on, 2x squared, right? Because square that whole thing, that whole quantity. And then over here is going to be 1.10 minus x, and there's two of them. So we can square that as well. All right, so there's the reason why I gave you 16. It's just you don't even need your calculator here. Just get the square root of both sides. Just do that in there. Might have trouble seeing that. Go back to you. That's fine. All right, so 4 is going to equal to 2x. What's wrong with my x? 2x over 1.10 minus x. Okay. We have perfect squares. We don't need the quadratic. And on your quizzes and tests, you'll never need your quadratic in our class. All right, let's cross multiply, get rid of these fractions, or you can just multiply. You can multiply through by the denominator. That's what that means. So 4. Whoops. All right, then we'll distribute there. 4.4. All right, let's add 4 to both sides. And so we're going to get 4.4 is equal to 6x. All right, x is going to equal, I'm going to need my calculator here, finally, 4.4 divided by 6. 0.733, on and on and on. Now, if you got this far, you got a point. 1 bonus point. All right, this is not the answer, is it? That's what x is. The question is this, asking what is the concentration of hydrogen chloride at equilibrium. That's right here. So we're going to just take that number that's in our calculator, multiply it by 2. And our final answer is going to be 1.466666 and so on. But we're going to round that to 3 sig figs, looks like. 1.47. With concentration, molar, or you can say 1.47 moles per liter, or you could say 1.47 moles liters to the -1. They all mean the same thing.